First talk of today's session. We're happy to listen to Victor Nador from Cracow in Poland, who will tell us about Jack polynomials and b-deformed constellations. So, Victor, the stage is yours.
Thank you, Ariane, and thanks to the organizer to give me the opportunity to speak here. It's my pleasure. So today I will speak about Jack polynomials and how they relate to, in the context of how they are connected to the enumeration of maps, and in particular to non-oriented maps. So the outline for this talk is rather simple. I want to spend some time to, first of all, discuss map in the simplest setup of the orientable case, and then to introduce two different types of algebraic generation that we can perform starting from maps. The first one is to go from maps to non-oriented maps. This will be related to the notion of b-deformation that will involve the Jack polynomials. And the second one is to go from map to constellation, where here we adapt algebraic point of view of maps, seeing them as factorization in the symmetric group, and constellation have a similar description. We can then mix these two generalization, and then we get the object that interests us today. That is the non-oriented constellation, on which we can additionally put some b weights, and this is the object we will study. I will present in detail at the end of the talk, and on which I will mention some results that I obtained during my PhD in a joint work with my supervisor, Valentin Monzon. Okay, so let's get started with orientable maps. So an orientable maps can be seen in different ways. One way to see it is that you take collections of oriented polygons and you equip them with a pairing, a matching on the set of their sides, so as indicated by the red arrows on my drawing. And so these red arrows tell you how to glue the sides of the polygon together in order to recover a graph properly embedded on a surface. So here, for example, if I perform this gluing, I get this map on the right that is drawn on the torus, so with genus 1, where we can see that the square is here and the octagon is around there. Okay. I think, okay. So combinatorists typically want to enumerate this type of objects with different types of weights. So for example, here I will denote F, the generating series for maps, with a superscript J for the maps of genus J, on which I put a weight T for the size of the map, so the number of edges, which correspond to half the size of the polygon, since they are paired together, and an infinite set of variables pi, which correspond to a weight pi for each face that will carry that will have length I. Then the first index denote the extraction of the maps of size n, and then after that the additional indices means that I'm working with a root face that has a given length k. So I work with a particular a distinguished corner and a face that is not weighted with p. So as is now well known by combinatorists, you can exactly enumerate the number of maps with these parameters via the so-called third equation. So the third equation tell you how you can generate a larger map of size n, starting from maps of size n+1. So there are different situations that can occur. The first one is when you have a map that has size n-1 with a larger root face, so of size k plus i-1. And then you can simply cut the root face in order to get a map that will have root face k plus 1 in the end. If you take two different maps whose sum of the lengths of the rooted face is smaller than k, then you can join them via an edge to form a root face that says k plus 1 similarly. And the third term is similar, but in the case of higher genus, so this will be absent for when you enumerate planar maps, but it's very similar to the previous one. So the first one is a kind of cut type. We cut a face in two, and the second one is a join type because we join two faces by a new edge. So these are sometimes also called the cut and join equations. And so what matters is really that they tell you what can happen when you insert an edge in a map. And you can actually rephrase, and so there is an infinite set, a countable set of equations indexed by the size of the root. So one for each integer. And you can actually rephrase this relation to write them as a partial differential equation acting on the generating series. In which case they are going to take this form. So you can see that you have an operator of order 2 in the derivative with respect to p that will correspond to the join case where we want to distinguish two faces. And the second one that takes the derivative, so marks a face of length k plus i-1 and corresponds to the cut case. So you can really recast the set of third equation as a countable set of differential equation that acts on your generating series. And when you write the equation under this form, you can check that these operators are going to form a Virasoro algebra, which is a bit abusive because actually, since we are working with a combinatorial model, we only have the positive modes of the Virasoro algebra, and also this is not so important, but the indices have to be shifted by -1, which doesn't change the commutation relation of the operator. And this is the type of relation that we will obtain at the very end of the talk when we will study the constraints for the b-deformed operation. So what's important here is that these constraints generated from the third equation, they're really close, they form an algebra, which means that if you try to generate, they completely characterize the generating series. You're not going to be able to generate new relations satisfied by your generating series from it, because this commutator closes, which is what we want to recover for b-deformed constellation. Okay, so now a second characterization of map that we need is that they can be described as a factorization of a permutation. So how does this work? Well, essentially, as I mentioned earlier, a map is a graph embedded into an orientable. An orientable map is a graph embedded into an orientable surface, and so you can use the local orientation around the vertices to describe the incidence relation between the edges. So if you are given a map, how do you find this triple of permutation? Well, first you label all of the edges, the half edges actually from 1 to 2n. So here I have 7 edges, so my indices range from 1 to 14. And then my first permutation is going to tell me what's the incidence relation around my vertices in green here. So I have cycle 1, cycle 2, 3, 4, 5, 6, 7, 8, and so on. Then my second permutation, alpha, is going to be a fixed point free involution that describes how the alpha edges are paired together to form an edge. So here I have 1, 2, 3, 5, 6, 9, and so on. And finally, the third permutation phi is going to encode the structure of the faces of the map. And so phi has to satisfy sigma alpha, which simply encodes the fact that if I go around a vertex, then an edge, vertex, edge, and so on, then I'm going to describe the faces of my map. So in this example, for example, you have a cycle one on the left, 2, then 5, then 9, and so on. So you can really describe this map as a triple of permutation that factorizes the identity with this condition that alpha has to be a fixed point free involution. But actually, you can relax this condition, and then you get the definition for an orientable map. So now it's no longer the half edges that are labeled, but it's the actual edges that are in my picture. They correspond to edges between the green and blue vertices. And so my second set of vertex correspond to these blue edges, which here are gonna all have valency 2 because I based my example on the previous non-bipartite map. And so typically in my previous example, I counted maps with a weight on the faces, which would correspond to have an infinite set of variables to count the length of the cycle of phi. But you can also add other infinite set of variables to describe the distribution of the green vertices and the blue vertices. And so typically the information will be encoded by the length of the cycle of your permutation. So if you want to do that, you can always sort these lengths by decreasing order. And so you can see that the information you care about is going to be encoded in a partition. And so from an algebraic point of view, we know that the ring of symmetric function has a basis its bases are exactly indexed by a partition. So here I use the French notation. And so for example, I represent the partition 6, 5, 3, 1 with this box diagram. But then there are different choice of bases that are, obviously they are equivalent, but they don't have the same property. So from a combinatorial perspective, it's natural to use the power sum basis. Why is that? It's because this power sum is the power sum basis is multiplicative in the sense that if you add a part of, let's say, for example, 5 in my partition, then it simply corresponds to multiplying by a factor P5. So this makes it very easy to count my parameter. But if I want to exploit the algebraic property of my maps seen as a factorization of a permutation, then the basis of the Schur polynomial is more fitted. So I'm not going to go into many details here, but it can be obtained from the power sum basis via a simple change of variable that involves the character of the symmetric group, which kind of relates to the fact that maps are actually factorization of the identity. And so if you try to write the generating series of map in that Schur basis, you can really make use of this property and of the algebraic properties that the Schur inherits from the character of the symmetric group to get a very simple expression for the generating series of map. So essentially, you have a sum of some numerical prefactor, a sum over partitions of a given size, and then you have 3 times the Schur function for each set of variable. So for the 2 sets of vertices and for the faces, evaluated on the same partition. And so this hints at the integrable structure that lies behind map models. So you can really see this type of map from different perspectives. So as I mentioned, using this algebraic definition, you can use the representation theory of the symmetric group. But also the fact, for example, the third equation I presented earlier relates to the integrability properties of some specialization of maps. And in particular, for example, you can also relate this to the fact that you can generate solutions to the KP hierarchy by specializing some parameters. Or if you like matrix models, then there's also a connection with Hermitian matrices whose perturbation expansion is the the generating series for maps, for some weighted maps with weight on the faces. Okay, so now what happens when we want to work with non-oriented maps? So now I'm simply gonna amend the previous definition for orientable maps, and now I allow my gluing to be performed while reversing the orientation on the side. So for example, this dashed edge means that instead of gluing the left corner here with the top corner of the square, I'm gonna glue the left corner on the bottom and the right one on the top. And so you can see that this creates a kind of Mobius strips when you perform the gluing. And so you're gonna obtain non-orientable maps that way. So for example, you can check that if you perform the gluing represented by this matching, this side matching, then you would get a map embedded on the projective plane. So here the northern part of this circle has to be glued with the southern part with the same orientation. And so for example, the square here ends up over there. So yeah, this construction pattern is not unique. For example, if you were to reverse all of the arrows, the dashed and non-dashed arrows, you would end up with the same map. But essentially, this construction behaves very well with respect to they behave very similarly to the orientable case. So you can also give an algebraic description for non-oriented maps, but this time it's not going to be described in factorization as factorization in the symmetric group, but it's going to rely on matchings. So if you take two different matchings, M and M prime, then you can form a graph made of the edges obtained from the two matching. It will be in general disconnected. And so you have a graph that whose cycle only have even ends. So you can divide all of the lengths by 2, and then you have an object that is also indexed by a partition. And how does that connect to the enumeration of non-oriented maps? Well, simply we take a triple of such matching, and we work with a quarter of edges. So yeah, with maps we had half edges. Here we have quarter of edges, and we have a first matching ME that tells us how the quarter of edges are paired together to form a half edge. Then a matching MS that tells us how the quarter edges are paired together to form the side of a face. And then the matching MC encodes the local structure at the vertex. And so similarly, we have a condition to get a map that the partition generated by the matching ME and MS should correspond to edges. So it should only have paths of length 2, so that when you close, when you take ME, MS, ME, MS, you want that to form an edge. But again, here you could relax that condition, and then you would get a definition for non-oriented bipartite maps. And yeah, in the non-orientable case, really everything works similarly as in the orientable. In the non-oriented case, everything works similarly as in the orientable case. So, for example, on the representation theory, you can describe the combinatorics of matching in terms of representation of the hyperoctahedral group. So again, you have a representation theoretic description, and you can also find the solution. This integrability property also translates in a similar framework, except that now you don't have solution to the KP hierarchy, but instead you have the BKP hierarchy. And in terms of matrix, you can also translate in that language, and instead of working with Hermitian matrices, you're going to work with a symmetric matrix. So you have these two, yeah.
I have a question about this BKP hierarchy, because I think a lot of different things are called the same. So here
it's
it's
the large BKP.
So it's like an integrable hierarchy that's where each equation is a deformation of the one in KP.
No, so it's the one that's larger than KP, but it's not a deformation. It's strictly larger.
So you mean all solutions to the KP hierarchy are also solutions to BKP?
Yes, exactly. Yeah, because I think what you're referring to is that there's a conflict of terminology with BKP, because there is one hierarchy which is called BKP that is actually a particular solution. I mean, it's constructed from a KP,
Yeah.
and the other one that's the other way around.
Okay,
so here I'm working with the one that's larger than KP.
Okay, so let's say the set of solutions of BKP strictly includes the ones of KP.
Of KP, yes.
Okay.
Yeah, it's the one that has a spinor description.
Yeah, okay. That kind of relates
the one of Katz and
I've
Vandeler.
heard of, but yeah, okay. Thanks.
Okay. And so, yeah, we have these two orientable and non-oriented cases that behave really similarly. And when you can find a broad diversity of, a lot of different structure and different point of view with a lot of results. But if you look closely at the theory, more closely at the theory of a symmetric function, you can see that there is a more general family of symmetric polynomials that encompasses both of those cases. And these are the Jack polynomials. So the Jack polynomials, they can be defined by the property that they are orthogonal to each other. They only expand over in the elementary basis. They only expand over the small partition. They have coefficient 1 and they only expand over smaller partitions. And this defines them uniquely. And so we essentially know when there are three values of B that are well known for this polynomial, which correspond to B equals 0, where they are simply the Schur polynomials and so are associated to orientable maps. And for B equal 1, where they correspond to zonal polynomial and to the non-oriented maps. So actually, there's a third value that is known, but it's essentially known through duality relation with the cases of non-oriented maps, which is B equal minus 1/2. So looking at that, it's natural to wonder whether you can kind of see this deformation in B as something that would measure how how non-orientable your map, how close your map is to a non-orientable map in some sense. In the sense that, like, if you put B equals 0, then you kill all of those contributions and you recover the orientable maps. So in particular, you can start from the definition of the Schur function that I gave earlier, and then you can replace all of the Schur that appeared in that definition with the Jack polynomials. And then if you go back to the natural basis to do combinatorics, which is the Poisson basis, you're going to get some coefficient here. The bottom line, the denominator is just a normalization factor, but we can look at this coefficient here. And if we want that the b-deformation correspond to a measure of how non-orientable the map is, then it amounts to saying that this coefficient here should be polynomial in B with a positive integer coefficient. And so this was the conjecture that was proposed by Goulden and Jackson in '96 that studied this generating series. And here, the main difficulty to attack this conjecture is that we have to handle three sets of parameters. So Q0, Q1, and P. So for the two sets of vertices and the faces. Over the last 25 years, there have been many partial results going in the direction of that conjecture by De Wenger, Ferret, Sniadi, Hussin, Bendali. But this conjecture in its most general form is still open to this day. So I'm gonna describe how we can be attacked from a combinatorial perspective. And for that, we want to introduce an additional statistics on our non-oriented maps that will allow to put a weight in B, to assign a weight in B to our maps to measure how non-orientable they are. And to do that, so I rely on the notion of a measure of non-orientability that was introduced by Guillaume Chapuis and Maciek De Wenger. And so this measure of non-orientability is simply a function that takes an edge in a map and assign a weight in B that must satisfy some constraints. So the first one is that the weight it assigns only depend on the connected component that contains my edge. And then we have different cases depending on how the two faces bordering the edge behaves. So if my two corners are in different connected components, so if by adding my edge I'm connecting two different connected components, then I want that this weight is always 1. If they are in different connected components, then in this case, there are two non-equivalent edges that can be added. So either you add a kind of straight edge, or you add an edge with a twist between C1 and C2 as represented on this drawing. In this case, we only want that the sum of the two edges weights 1 plus B. So this gives a lot of freedom for the choice of row. And if the two corners are in the same face, then we can simply compute how the number of faces evolves when we delete the edge E. And we want that it has weight 1 if the resulting map has, the map obtained by deleting E in M has 1 face less than M, and we want that it has weight B otherwise. So the first case corresponds to the cut case of the third equation, and the second one corresponds to adding a twist or a cross-caps structure within a map. And so just to have a model on which you can actually compute things, I'm gonna make the second definition more precise by imposing that if my map is orientable, then I want the weight to be 1. So essentially, by playing with this condition, this gives an explicit formula to compute the weight for all maps. Algorithmically. So essentially, what you do is, if you are in the case B, then you can check what happens when you in the same map with the twisted edge, and on a map that is orientable, then you know that's always gonna have weight 1. And then you can come back to the map you had to compute its weight in B. Okay, and at first sight, this definition may seem rather innocent, but it has dramatic consequences on the enumeration of maps. So why is that? The first thing is that the polynomial, the weight in B that you're gonna get in a map really depends on the order in which you delete the edges inside the map. So for example, here you have a very simple bipartite map. So it's a kind of minimal examples that showcase this feature. And so depending on if I delete first the vertical edge or the horizontal one, I'm going to get 2 different weights in B. So let's say, for example, that I start by deleting the horizontal edge. Then I'm in the case C, because my map initially has 1 face that goes here. Like this and that side. And you can see that when I delete the horizontal edge, then I'm still going through the cross caps on the top. So the resulting map still has 1 face. So I'm in the case C where I had a weight B. And then when I delete the second edge, I'm I'm still in that case. So in total, I'm going to have a weight B2 by deleting first the horizontal and then the vertical. Now, if I do the opposite, I start by deleting the vertical edge. And then I can check that if I had added a vertical edge, but if here the gluing was performed in the other direction, then I would have obtained a map drawn on the torus. And so I know that in this case, I would have had an orientable map. So I know that here I should have weight B. But then my horizontal edge is, I mean, here at this stage, I have an orientable map. So I know that I'm going to have weight 1. And so you can see that in this case, I only have weight B. So what this means is that to properly collect the weight in B, I have to be careful of to watch out about the order in which I am deleting edges. The second information that's important is that contrary to what we may think at first sight, a rooted map and its dual won't give the same polynomial in B. So here, for example, is an example that showcases properties. On the left, you have B polynomial B squared plus B cubed plus B squared plus B. Whereas here you have under its dual, you have B cubed plus 2B squared. And this may seem innocent, but we'll see later that to properly compute the B weight of our objects, we really want this property. We need to alternate between the map and the dual. And so this can be a source of, this is a source of additional difficulty. And so actually this was known since the work of Michael Lacroix, which can be found in his PhD thesis, where he states that a measure of non-compatibility on maps, it cannot be both additive for connector, which is something that I took earlier in my definition for the measure of non-compatibility, and invariant with respect to the duality for rooted maps. So essentially what this tells us is that with this definition of a measure of non-compatibility, there is no chance to have duality invariance at the level of map. I mean, by looking at one map and its dual simultaneously. Okay, so now I'm going to introduce the constellation. So the constellation, they generalize the algebraic definition for maps seen as factorization of permutation, but to an arbitrary number of permutations. So now instead of just having sigma alpha equal to phi, I take muplets of permutation, and I just simply require that this factorizes phi, or if you want that the muplets phi minus 1 is a factorization of the identity. So in constellation, the notion of edges is replaced by hyper edges, which correspond to my blue polygons here. So here I drew a blue constellation. So yeah, the red corresponds to color 0, green color 1, and blue color 2. And so what matters is that in my faces are going to be my white polygons. And so if I go around red, green, blue, then I will describe my faces. So for example, here I'm describing the outer face. So here I think I should have 3, 5, 10, 1, like this. But essentially the game is similar as in the cases of maps. What's important with constellation is that seen like this definition depends on the base choice of orientation for the surface, because I need my hyper edges are going to have one vertex of each color visited in a very particular order. So for example, here in the clockwise order on my hyper edge, I'm going to visit 0, 1, and 2. And this is a problem to define things on a non-oriented surface, because I want things to be independent of the orientation of my surface. And so one way to do that was found by Chapuis and de Wenga, who introduced non-oriented constellation. Oh yeah, sorry. So yeah, so as they generalize this property of factorizing the identity, they really take a similar form as in the maps, in the sense that like you again have a sum over partition, and then a product of a Schur function evaluated on the set partition. Okay, so now if I to make the constellation independent of the base choice of orientation, what I can do is that I can merge together. I mean, essentially delete all the edges that connect a vertex of color 0 with a vertex of color 2, and merge together an hyperedge with the adjacent face like this. So here, for example, and what you would get is then that. So now your face don't cycle from 0 to k, but they go from 0, so 0, 1, 2, and then they decrease, so 2, 0, 1, 2, 1, 0, and so on. We can show that this is a good generalization of non-oriented maps because, for example, this object can really be described as k+2 applets of matching, as was shown by Hussein in a paper of 2022. And now that we have a non-oriented model for our constellation, then we can assign B weight to it via the notion of a measure of non-orientability. So to do that, Chapuis and Dowenga in the article describe an algorithm that allows us to do so. So how does this work? You start from a root corner. So for example, let's say my root corner is on the top here, and I give it an orientation. And then I'm gonna delete the path that follows and that goes up to the vertex with the highest color. So in my example, I will delete this and that. I collect the B weight with the rules that I gave previously. And then I move on and I delete I keep doing that until my vertex is deleted. So here we delete that edge and that edge. And finally, we delete this and this. And then I completely remove this vertex from the map. So when I've done that, I have to, and at the same time, I have to keep track of how the size of my root face evolves. So when I've done that, I end up with a constellation that has one vertex of color 0 less, and that has a root face of a given size. And so now I want to iterate the algorithm, but I need to iterate it on the dual of the constellation that I obtained. And so you can see this is why it makes the identification, I mean, this connects to the difficulty that I mentioned earlier of the B weight not being invariant via duality. And so for this reason, actually making contact with the Jack polynomial is really non-trivial. So in this paper of Chapuis and Dowenga, they show that the combinatorial equation you get for this model actually corresponds to the same equation, but for the generating series of Jack with certain specialization. So what they show is that they can work with two full sets of parameters, that they will keep track of vertices of color 0 and of faces. And for the intermediate color from 1 to k, they give it a weight ui for each vertex of color I, and this corresponds to taking the principal specialization, which means that every variable for this set of variables is evaluated in UI. And so the equation they give is this equation here on top. And so you can interpret it combinatorially, and it has a nice combinatorial interpretation, because this just tells you that if you start from a given constellation, how you can insert a new vertex of color 0 in it. So essentially, this equation is the opposite of the algorithm that computes the B weight. So you're going to try to, you want to insert this vertex of color 0. First, you're going to connect it to a vertex of color 1 in green. And you're going to use a catalytic variable to keep track of how your root face is growing. So yeah, you can either connect to an already existing vertex. You can also create a new vertex as showcased here. And you iterate the operation until you finally reach a vertex of with the highest color possible. When your insertion will give valid constraints, in the sense that all the vertices of intermediate colors will have neighboring of colors I-1 and I+1. And yeah, vertices of color 0 will only have neighbors of color 1, and vertices of color k+1 only neighbors of color k. And this equation, so it may look quite complicated at first, but it's because it involves this operator lambda y, but this is essentially an extension of the cut and join operator, which includes a term for the non-orientable case here and here, and the b-deformation that is weighted properly, so with respect to the rule that I gave to define the measure of non-orientability. And so yeah, when you look at this top equation, this is very similar in the orientable case to a sum of third-like equation, in the sense that what you're doing is you're essentially keeping track of how the root face evolve. And at the very end, you forget that you were working with the root face and you replace it with an authentic p variable. So when you look at that, you can really kind of think of this equation as containing a countable set of third-like equation. And this is why we wanted to, so with Valentin Bonhomme, we wanted to look at this equation to try to extract constraints starting from this equation. And actually, this is something that you can do under some technical condition. So essentially, you say you have an equation of this form. So the derivative of your generating series with respect to t takes the form of a sum of monomials in t to some positive power, and a differential operator in p and its derivative. Then this lemma states that if you can identify the third-like constraints, so derivative with respect to pi and this operator minus the sum of this operator in M, if you can identify this operator and if this operator are closed under commutation. So here, this operator, they don't, I mean, they need not to form a Lie algebra, but they only need to be what would be akin to a structure constraint in a Lie algebra are not, because this operator D, they can actually be differential operators in B. So they only have to be in the ring of operators in Pi and the derivative with respect to Pi. What matters is that the bracket closes and can be re-expanded over the initial set of constraints. So provided you can identify this operator and you can check that they behave as you would expect the constraints to behave, in the sense that their commutator closes, then you can actually identify this operator as constraints. So just as in the orientable case, you would have that each of these operators annihilates the generating series. And again, this comes from the fact that essentially this operator would describe how your series is behaved order by order in its size parameter. So what happens when you increase the size of your map by 1? Okay, so now we wish to apply. So yeah, this method has the huge advantage to be valid for all values of B. So it really allows to circumvent all of the technical difficulties that are related to the introduction of the b-deformation. But the difficulty is that then it requires to be able to identify MIK, which in this case is not too difficult, but also to be able to compute the commutator, which is where the main difficulty of this lemma lies, because essentially you have to, this tells you that if you can check that your operator behaves as constraints, then you can legitimately identify those operators as constraints. Okay, so let's try to apply it to the non-oriented constellation. So in this case, it's pretty straightforward to identify our operators M, because just looking at the form of the equation, we have something that's already on the correct form. One difficulty, one restriction is that we have to specialize the second set of variable qk so that it's non-zero on finitely many indices. This is just a technical condition to be able to apply our lemma. And then the third step is that we have to compute the commutator for this operator. And the complexity of the computation will depend on how many times you apply this cut and join like operator. And so you can see here that it will appear at most n-1 k times. And in practice, we were able to deal with at most cubic constellations. So this includes bipartite maps and geometric maps, as well as face-weighted three constellations and trivalent bipartite maps. So here we only have one set of variables that will be on the faces for each of these models. And then you can combine those that you can combine. So for example, you can take here you would have Q2 non-zero and here Q3 non-zero. But obviously you can combine the two and we are sure that this will remain well behaved. And so now the final step is simply to compute our commutators. So in the case of bipartite maps, things are not too difficult, and you can check that we get, unsurprisingly, Virasoro algebra. But in the case of three constellation, the computation is much lengthier, and it relies on several tricks because you have to cut each of your contribution into several pieces and rewrite them in a clever way using commutation relations between your operators. And at the end of the day, after a bit of effort, we managed to show that so this commutator indeed closes. As you can see here, it's re-expanded over. So the large J are simply either multiplication by pi or derivative with respect to pi. So as you can see here, we don't really have, this is not a Lie algebra, but it is an algebra nonetheless. And this is sufficient to apply our lemma. So yeah, one point I should stress with this computation is that because of the technicality of the computation, we don't even know how to put those constraints on a computer to automatize the procedure at the moment. So that's the main limitation of those work this day. But nevertheless, for the maps and the three constellation, we can actually find a set of operators that we can indeed identify as constraints, so formed by this operator mi, with an explicit form and an explicit form for their commutator. So when you look at the previous literature, so for the maps, these constraints were already known via the equivalent for the b-deformation from the point of view of matrix models. So which is the notion of beta ensemble, which, for example, can be found in Adler and von Morbeke. But for cubic constellation, in the case of constellation, much less was known. So these constraints were known for in the orientable case in Fong's PhD thesis, but for example, the algebra was not. So in this case, this is the first type of results that shows the algebra of constraints for constellation, and in addition, we already have them for arbitrary B. Another interesting consequence of this work is that so our constraints involve this operator I derivative with respect to pi. And so what this tells us is that this operator can actually be interpreted as a marking of a face of weight of length I in a map, which was not obvious at all because of this lack of symmetry of the B weight with respect to duality. So what this seems to hint at is that there should be a form of duality that holds on the geometric series of constellations, so extending the role of the faces and the vertex. But it should be more refined than a simple map-to-map duality. Maybe my personal take is that it probably holds, but at the level of maps with a given profile. And if you look at the set of maps with a given profile, then you can probably match the the set of value taken by the B weights in those maps with the set on their duals. And so yeah, what can we do from here? So there are different several things, I think. So the first one that we are currently working on is to try to extend these results, but to have a better computation method that will allow to extend these results to any combinatorial model. So for that, we have an idea, which is to use a computation technique that is inspired from a conformal field theory, which is the operator product expansion, but adapted in this combinatorial setup. And more generally, I would also be interested to investigate this integrability property for the Jack polynomials. So, for example, one question that I had is whether there is an algebraic description. So what I had in mind was, that I still have in mind, is whether there is a group theoretic description of the b-deformation. So in that direction, recently there was a preprint on arXiv by Chidambaram, Dowenga, and Oshuga, which describes these constraints as a W algebra, so something much more powerful than what I was hoping, but that's already something in the direction. And a second question that, in my opinion, to my knowledge, hasn't been studied at all, is whether there exists an integrable hierarchy, so similar to the KP or the large BKP, that would hold for generic values of B, at least for this model. So yeah, these are questions that I hope to investigate in the future. So that's what I wanted to present for today. So thank you for your attention.
Well, thank you, Victor, for the nice talk. Are there questions from other people? If not, I have a few, but don't hesitate if you have some.
Yes, I have one question.
Go ahead.
Right. So the operators L which appear in the constraints, they are indexed by 3 integers, right? So there is M, which is the number of colors of the maps in the map. So whether it's bipartite maps or constellations. And then, so the K is the degree of the vertex we are adding, or is it something else?
Yes, K corresponds to the size of the vertex you're adding. Absolutely.
Okay, and so the constraints that you obtain in the slide just after, so K is always equal to 1, or so the difficulty, it comes from M and K, right?
Yes, here on this exact slide, I only have K equal to 1. Okay. But in practice, we can do it for some other models, so we can do it for K equals 3. But actually, these two models are quite similar. I mean, they behave similarly, the two cubic model, or K equal to 2 here.
And the integer in the subscript, so it corresponds to what exactly? Can you recall the...
Sorry, which one?
So the subscript of the operators L. So there is a I and J.
Okay.
So
yeah, so
combinatorially...
it corresponds to the size of the root face.
Okay,
that you're building.
Thank you.
Thank you.
Yeah, so about these operators J again. So there's no, do you have a nice general expression? Because you said that they contain some derivatives with respect
to
they
have a very simple expression. So they are just either, if the index is negative, then they are simply a multiplication by pi. And if the index is positive, they are derivative with respect to pi.
Okay, so
it's just a notation it's just a notation to make things simpler, essentially.
Okay. So
it's the usual current operator.
But that's you were saying that it's already complicated enough that you can't really use computer algebra to, for instance, check that it stays in the algebra and stuff like that.
Yeah. At least maybe there's a way to do it, but I I just missed it, but essentially the trick is that to show that this closes, you really have to rewrite each of the terms using the commutation relation either between J and L or between J themselves and stuff like this. And so you really have to do a non-trivial rewriting to be able to get the right-hand side here and to recast everything as a function of L. So if you take the left-hand side and you naively expand, you're not going to ever get something that looks like a sum of LK terms.
But can't you, like, I mean, like, there is a precise set of commutation relations that you're going to use, so you can't implement that kind of algorithmically, like try each of the possible commutation relations.
Yeah, but then how do you, then I think the problem is that you wouldn't know when to use what commutation relation.
I see.
But well, yeah, hopefully our new idea will allow us to bypass this difficulty. It remains to be done for now.
Thank you. Are there any more questions? Well, if not, let's thank Victor again.